Good evening all. Welcome to week 10th of the problem solving session. So this week we will be solving problems regarding convection and diffusion, convective diffusion equations. So we'll get started with today's session. The first question is essentially about the boundary layer equation. It asks you to discretize above equations on a 2D Cartesian mesh, considering the values of velocities are stored at the phase centers. Like it is explicitly mentioned that the velocities are stored at phase centers. In the next week, we will be solving using simple algorithm where your velocities will be stored on phase centers and your pressures will be stored at the cell centers. So let's get started with this question. So the governing equations are given the continuity equation, and we also have the momentum equation, in absence of pressure gradient, and these are just the boundary layer equations. We need to discretize this over a domain. So say suppose it's over a flat plate. So we are considering a rectangular domain. And we are using a Cartesian mesh. So we will follow the usual strategy. So we will consider some interior cell first, and then we will look at boundaries. Okay, we shall write the boundary conditions as well. So here we have two unknowns. And we have two equations. So this should, in principle, can be solved. The next question comes is, so how many boundary conditions we need to have? So it is first order in so if you see the equation, it is first order in x and second order in y. So we need to appropriately write the boundary conditions. So if we see here, so along x, what are the boundary conditions we have? We know u. So for this rectangular domain shown here, so if we have to write the boundary conditions, at the bottom face we have u equal to 0, this is no slip, v equal to 0, essentially because there is a wall there and nothing is actually it's impermeable wall. And on the left side we have u equals u infinite, or essentially your inlet velocity in flow conditions, and your v is essentially 0, that we are saying this is the starting point of the flat plate. So before touching the plate, everywhere the velocity is u infinite and v is essentially 0. And on both the top face, we are assuming that it is hyperkilometer, which we will see later. So what we mean by this is essentially along this direction, we will come to this. So what I meant by high Pecla outflow condition is essentially your Pecla number is given by it's the ratio of convective to diffusion. So when I say this tends to infinite, it essentially means the effects of diffusion are tending to 0. So we will first formulate our problem for this particular case, and then we will see in other problems where the outlet flow conditions will also be specified. So we will start with this assumption. So first step is we will consider a grid. So for an interior cell, we will write for an interior cell, and then we will move on to the boundaries. So in a 2D grid, this is my interior cell, these are my neighboring cells, these are my faces. So the first, we will start with the continuity equation. In the continuity equation, we have del u del x plus del v del y times dv. In this particular case, for simplicity, let me write it in this. First one is del dot u dv is essentially 0. This boils down to, if you use the Gauss divergence theorem, this is essentially u dot dA equals to 0. Now anyway we will be replacing with this will be replaced as sigma uf dot af equals to 0. So now on the faces, what will this give us is essentially, say for the pth cell, u east times for the east cell, for the east face, if this is delta y and this is delta x, and say it is a uniform grid, u east, the area will be perpendicular to it, so it will be u east times delta y minus u west. For the west face, for the east face, we have delta y I cap. This is for the east face. Similarly, for the west face, the area vector will be pointing in this direction, that will be delta y minus I cap, u west times minus delta y, since we are assuming all these velocities are in the positive direction. And then we also have along the north direction, we won't be having the u component, we have v component, so vn times delta x plus v south times minus delta x should be equal to 0. Now as per the notation that been used in the lectures, we call this as Fv minus Fw plus Fn minus Fs equals to 0, where these F's are essentially the flow rates. In this particular case, the density term is not there, otherwise it will be considering rho times u times A, only the magnitude of the area vector, and the signs here will take care of the remaining ones. So the continuity equation gives us this particular discrete equation. Next step is in the momentum equation. So when we go to the momentum equation, we have integral, or let me write in that way. So we have del dot u is essentially given as del dot mu x times del u del x plus mu y times del u del y, where however in this particular case we have mu x to be 0, mu y equals mu. So if we compare this with our scalar transport equation, we can see this is the convective term and this is the diffusive term, and there is no source term. So if you would have had a pressure gradient term, then that would be contributing to the source term, so which you do not have. So we'll start discretizing this. So first step is you multiply over the volume we have. So since we just have the one equation, I will just write it as integral mu del square u del y square dx dy, or let's just say dv, or we'll substitute that later, so we can just write it as integral del dot mu x del u del x plus mu y del u del y. Now if you apply the Gauss theorem, this essentially becomes what dA bar equals, this will again give you mu x times del u del x. So if I write it as this, plus mu y del u del y on the face times af bar. So which if you further simplify, we can write the final equations directly, since now you are familiar with the method. This will essentially give you sigma, the uf bar dot af bar over all the faces, sigma mu del u del f, del u del y evaluated at the face times af bar. Now if you were to see this particular term here is essentially your f. So if when we write it as for each individual faces, so for the f east times u east, and for the west face the area vector will be in the opposite direction, f west times u west plus f north u north minus f south u south. On the right hand side we have the normal diffusion term that we were used to have, so that will essentially give mu times, since it is along the y direction, say it's along the y direction, so your area will be, since say it's on the north face, so your area will be delta x. When it is on the south face also it will be delta x. So you have mu times del u del y, since only the j cap term will be there and there is no mu x in our particular case, in which so your I cap terms will be going. So you have mu del u del y on the north face times delta x minus mu del u del y on the south face times the area is delta x. So this particular terms can again further be written as, like we were used to this, so we can write it as d naught times u north minus up and d south times up minus u south, where d naught is essentially mu times delta x by delta y and d south is essentially the same. Now the next thing is, we are on the LHS we have something on stored at the phase centers, while on the RHS we have something stored at the cell centers. So the next step would be to convert your phase centers into cell centers. So how would we go about do that? So there are different schemes to it. So we will start with the central difference. What we do in central difference is very simple logic, where so I'll just do for the east coefficient and the similar steps for all other coefficients as well. Say when you have the, so this is my P cell, this is my east cell centroid, and this is my east phase centroid. So we are approximating u little e to be up plus ue by 2. Similarly for all other cells. So if you were to replace those in my original equations, the equations become fe times minus d south times up minus us. So if we group the terms together, we will group up terms equals u east. So we can write this in our standard form, where ap up essentially a east u east, or sigma a and b u and b plus b, where our b term is essentially 0 in this particular case, since we do not have any source terms. And if we see the coefficients for a east, so we have nothing from the diffusion, but we have a minus fe by 2. So essentially what I am trying to do is group the take all the up terms towards LHS and then all other terms to RHS. So group up on LHS, u and b on RHS. So that will essentially give me a east to be minus fe by 2, a west will be fw by 2, A north, I have both the diffusion as well as the convective one. So I have a dn on the RHS, and then from the LHS we have a minus Fn by 2. And A south, on the RHS I have a D south term, and then from the LHS I will be having one more term, Fs by 2. And then if we collect the terms for AP, so we have a dn plus ds coming from the RHS, and on the LHS we have plus Fe by 2, W by 2. So as introduced in the class, we will follow the same notation where we have dn plus ds, and then we also have, we will write it in a slightly different way. So we will put it as, what I was trying to do, what I am trying to do now is to express AP as summation A and B. So I'm just grouping terms together so that we will see the AN and AS terms. So if you see, dn is coupled with minus Fn by 2, and ds is coupled with plus Fs by 2, and in addition I am having A east is minus Fe by 2, A west is Fw by 2. So what I have done, I have subtracted Fn by 2 minus Fs by 2 just to make things, so I am just adding and subtracting this particular quantity just to compensate for this, and then I have my original terms coming from the top, Fe by 2 minus Fw by 2 plus Fn by 2 minus Fs by 2. So this now boils down to our original form, where you have AP sigma A and B, plus you also have some additional terms. These are my convective terms, Fe minus Fw plus Fn minus F south. What is this term exactly? If you were to see the original equations, this is equation number 1, which is the continuity equation. So this is essentially your continuity equation. So for an incompressible flow, you can see that this term will essentially go down to 0. So this comes to our standard form again. So AP is essentially sigma A and B. So for all the interior cells, we have this particular kind. Now let us see what happens on the boundaries. So we will start with the left boundary. So the standard equation is again the same. So we have F east though I am writing the equations in this particular form, you might have observed that f itself is a function of u, which is an unknown. So what we do is we start with an initial guess and use that initial guess to populate all these Fe values and then determine u, and then keep on iterating that. That is something we will do later in simple. For now, just assume that this is based on some previous iteration value. I am just removing star because it will be present everywhere. So you have Fe times ue minus F west u west plus Fn un minus Fs us will essentially give you the same equation. We don't have any, so d east will be there, but then you don't have u terms here, so times 0. You don't have any contribution from east and west terms because of diffusion, because your nu x is 0, or to say, or maybe I write here. So we have d and dn written in this way, and then d is essentially 0, d west is essentially 0. Otherwise the equation would be something like d little e phi east minus phi p, and then you will also have a term from west, phi p minus phi west. Sorry, in our particular case we don't have u, we have u east minus up, up minus uw, and then we have dn term that adds un minus up, and then we have a d south, that is up minus u south, and then any other source terms which we have, which we do not have any source terms, so I'll just put it 0 here. So in our particular case we don't have these terms, so dE and dW are essentially going to 0 because the diffusion flux is viscosity is 0 along that particular direction. So now if we try to, before trying to group the terms together, we will see the boundary condition. So the boundary condition says u is u infinity and v is essentially 0 on this particular boundary. So we are storing on these cells, so Vs and Vn or something that we cannot say at hand, but uw is essentially known. So our equation becomes ue minus fw times u west boundary plus fnun minus fsus, and remaining all will be the same. So you have un minus up and then a south contributing term. So again we will use say central differencing scheme. So you essentially place ue with the mean up plus ue by 2, on the north face you will replace with up plus un by 2, and on the south face you will replace up plus us by 2. But then on the west face uw is replaced just with the boundary value. So now this is essentially a constant, so this term will essentially go to your b term. So now when I write my coefficients AP as sigma A and B plus B, all my previous coefficient will remain same. So my A east will be D east essentially 0, so minus Fe by 2. A west is 0 because we don't have anything on the west boundary. A naught will also be similar, so we have a Dn term and then an Fn term, and A south, sorry, so this is a minus, and then A south we have D south plus Fs by 2, and your AP, if you write the AP terms, so it will be, we have a Dn plus Ds plus Fe by 2 minus, we don't have an west coefficient, we have Fn by 2 minus Fs by 2. Now if you were to write it in our original form of sigma A and B, so this boils down to Dn minus Fn by 2 plus Ds plus Fs by 2 minus Fe by 2. We don't have a west coefficient, so plus 0 plus Fn by 2 minus Fs by 2 plus Fe by 2 times we have the same term here. So what this gives us is sigma A and B plus F east minus F west plus F north minus F south, which we have always, and then we have one more FW. So this last FW is essentially to compensate for that this minus FW that is in our standard way. So when we write the coefficients for here we have a Dirichlet boundary condition. So in the case of Dirichlet boundary condition, what is essentially happening is in this particular scenario it is on the u and our d is 0, so we don't have any term adding because of diffusion in your A and B term. Otherwise you will have one more additional term coming up here in the east coefficient, which is not present here right now. So we'll get to see that as well in the coming up example. So this is your AP, and then previously we did not have a B term, but now we have a B term that is essentially coming from the west boundary, FV, FW. So this is your B term. So this is for the left boundary. Now similarly, if you were to write on say bottom boundary, Okay, it's already half an hour. Okay, so if you were to write on the bottom boundary, so you have this is my P cell, this is my south face, east face, west face, and north face. So we'll write down the equation straightforward. So the writing equation is straightforward. So we have f east u east minus f west u west plus fn un minus f south u south. So we are writing for the u momentum equation. So this is again the same, Vn minus Vp plus d south, sorry I got used, it will be u north minus up plus d south, u south minus up. So now here in this particular case, though we have a no slip condition, so this particular term here we do not have a south cell centroid, so this term has to be changed essentially. So like we do in our Dirichlet condition, so whenever we have a Dirichlet condition, what we were doing previously is, when you have your gradient term, this is your gradient term del u del y on the south face times area, here area is delta x. So what we were doing previously is mu times delta x by delta y up minus us, but this particular formulation is not possible in this particular scenario because we have a boundary here. So how do we replace this? So same as we do previous in conduction, so we just take the half cell, so delta y will be replaced by delta y by 2, and then you have up minus u south boundary. So now you have something so we write this as our diffusion coefficients are constant, so we just write 2 times ds into up minus usp. So now if you write the equations, so remaining everything else will be same, so use the central difference scheme, multiply 2, and then on the west face and on the south face, u south is something we know and it is a no slip condition, so essentially the term goes off. This is essentially dn times un minus up, and then we have ds replaced by 2 ds into u south boundary minus up. Now if we group the terms together, a east is again the same, is minus fe by 2, a west remains the same, so we don't have diffusion term, a north remains the same, so we have a diffusion term un, and then a south will essentially be 0 because this is the boundary. Now we also have a b term coming because of your Dirichlet condition, but in this particular case your south boundary is so like the b term is essentially 2 ds diffusion times your boundary value. In this particular case, because of no slip, this term will go out to be 0, otherwise you will have this term, and then you have ap will be essentially dn. Then previously we used to have a ds, but now we will be having 2 ds, so that the additional ds is coming from your boundary condition, so because of your Dirichlet condition, and then we have terms from the other hand, so we have minus fe by 2, sorry, plus fe by 2 minus fw by 2 plus fn by 2 minus fs by 2, and this used to be there, but in our particular case the term goes off to 0 because it is on the south boundary. So we write this in our coefficients, so it will be dn minus fn by 2. We don't have a south term, so I'll just leave that south to be 0, and then on the east face we have minus fe by 2, and on the west face I have plus fe by 2 So if we add these two equations, so we will be left with Fe minus Fw plus Fn. Ideally we have a minus Fs, so I will just add one Fs term here and then also a 2ds term here. So I am having sigma A and B plus F east minus F west plus F north minus F south. In addition, I am having this term. So this is coming because of the Dirichlet condition, and this is coming because of the convective condition. I mean, this is coming from, both are coming because of Dirichlet condition, and one is the convective term, the second one is the diffusion term. So if you see, the point I want to highlight here is this particular expression remains the same. So when you are doing it programmatically, how do we approach this is, we write the normal terms. So if you observe the normal equations, so A east can always be written as d little e by F e by 2, and A west can be written as plus Fw by 2, A north and A south is essentially plus Fs by 2. This is for your central differencing scheme. Later on we will see other schemes and quite a general way of writing these expressions programmatically. Now once we have the coefficients, like the first step is to essentially get your diffusion coefficients. So okay, maybe I should have written this later. First step is to get your coefficients. dE is essentially gamma E in our standard convective diffusion form, so it will be delta x by, for the east phase your area will be y, so delta y by delta x, and dW will be gamma W, d north Once I fixed my diffusion coefficients, the next step is to fix my convective coefficients, determine my convective coefficients. That is again straightforward. In our standard convective diffusion form, Fe will be rho east u east, and for the east phase the area is delta y. I am just taking the magnitude of this, following the same notation as used in the lectures. So Fw will be rho w uw delta y. Fn is rho n vn delta x. Fs is rho s vs delta x. Now that we have d and all the diffusion coefficients and the convective coefficients, we write our equation coefficients in this particular way, and the value of AP, so I am writing this for a general way. So if you have a convective diffusion equation of this form, it's for some scalar transport equation. So we have del dot gamma del phi, and if the source term is also present, so say we have something like SC plus SP phi, so we have linearized the source term already and it is of this particular form. The first step is we get the diffusion coefficients and then convective coefficients, and then we write our all the A and B's for series or in any general scheme that you do, and then your AP is expressed as sigma A and B. This is what we were doing previously. In addition to the normal one, minus we also have source term, and then now we have our convective terms coming into picture. So we have F east minus F west. So this will ideally be 0 because of your continuity equation. So we are dealing with incompressible flow, so this particular term will anyway go to 0. But so once you define your coefficients, your A and B is this, and your B is essentially SC times delta V. This is a standard. Now say suppose you have to implement some of these boundary conditions. So the first boundary condition you will be dealing with is Dirichlet. Say you have Dirichlet condition on say east face, on the east boundary. So naturally, since it is on the east boundary, your A east should go to 0. So what I do is A east will go to 0 and all other remaining coefficients remain the same. So these remain the same. So my AP is, again I'll use the same formulation, so it will be A and B minus SP delta V plus F East minus F. So everything else will be same. This is a standard form, but now that A East has particular is going to 0, and then we have a Dirichlet condition. Because of the Dirichlet condition, like we have seen previously, there will be some additional terms coming up. One, because of the diffusion, in a Dirichlet condition we will have a delta y by 2 at the boundary, because of which we will have a 2 times d coming up here. And then on the boundary we also have an F East term coming up, and that F East term should ideally be not be present because we know the value of the boundary, but here we have added that term, so it will essentially get subtracted here. This is on the east boundary. Say if you are writing on, say, west, say the south boundary. So west we have, okay, we have already written for south boundary above, say, so now maybe we might have to write for, say, west boundary. So the idea is simple. In the west boundary, if you have a Dirichlet condition, A west will be 0 and all your remaining coefficients will remain the same. They remain the same, and your AP will now be written as sigma A and B, which only includes these terms because A west is 0 minus SP delta V plus your continuity FE minus FW plus Fn minus Fs. And now because of your Dirichlet condition, you will have one additional terms. It is on the west boundary, and because of Dirichlet you have 2 times dW, and then we also have Fs term that is getting subtracted here, which should not be there because of Dirichlet condition, so you will have an additional FW here coming up. Now because of your Dirichlet condition, you also have some other terms in your B. So ideally you would have SC times delta P. Now you have a diffusion term, so that will add to your east boundary, and then in this particular scenario you also have an F East term that is also contributing to it. So your F East times phi east bound. So your B term will also get these 2 additional terms. Essentially whatever is your coefficient here times the value of the phi on the boundary will be added to your source term. So in this particular scenario you will have SC times delta V, and then you have 2 dW plus FW times phi west boundary. Similarly for the now north and the south boundaries. So this is for a Dirichlet boundary condition. Now suppose you are having a different boundary condition, say you have a Neumann condition. So it essentially says your flux is 0. So when your flux is 0, your diffusion term just goes off. Say I'll write just for one boundary, say on the east boundary, if you were to write only on the east boundary. So your A east will be 0, remaining everything remains the same. So I will write AP in again the standard format. So you have sigma A and B plus F east minus west plus north minus south minus SP delta V. Now there won't be any diffusion term coming up because I said the boundary condition is a Neumann condition. However, the diffusion term will be 0. So this is my east boundary. I don't have an east term. So if my diffusion, say here it is a Neumann condition, so which essentially means the gradient here should be 0. That will essentially give you phi east boundary to be equals to phi p. So this term will be added to your AP term. So maybe I'll write the equation. So you are having essentially phi east minus FW phi W say in our particular case we don't have east and west terms, we just have north and south. So in this particular equation, what this Fv will essentially be equals Phi, or in our case Phi is replaced with U if we are writing for the x momentum equation. So this will be Up minus, if we are using central difference, so this becomes Uw plus Up by 2. And remaining everything else remains the same, Un plus Up by 2, and then you have Us plus Up by 2. Now if we see the term, so since it is on the east boundary, your A east will essentially be 0. Your A west remains the same. So A north will be dn minus fn by 2, and A south will be ds plus fs by 2. But your AP, if we group the coefficients together, so we have a dn term, df plus ds. On LHS we have an FV term, and then we have minus fw by 2 plus fn by 2 minus fs by 2. So if we group these terms again to write in the form of sigma A and B, so we have dn minus fn by 2 plus ds plus fs by 2. Since I have made some changes here, so just to compensate for them, minus fs by 2, and then I have a west coefficient of fw by 2 that I have added, so and then I will subtract that, and also have fe minus fw by 2 plus fn by 2 minus fs by 2. So I am just taking this here, so this is just to compensate these terms. So this is your A north plus A south, these two will give you those terms, and then the last one will give you this particular coefficient is A west. Now we are left with Fe minus Fw plus Fn minus F south. So this is again comes to our standard form, sigma A and B plus Fe minus Fw plus Fn minus Fs. So the only so this is very similar to what we have discussed in the conduction equation as well. So when you have a Dirichlet condition, you will have these terms coming up in your AP as well as in your B. But when you have a Neumann, you don't have any terms coming up in your AP term, so it will be the standard form, and your B also won't have any additional terms coming up because of this. So your B will essentially remain the same. If you have a source term, it will be SC times del W. You don't have any additional terms coming up like you have in the case of a Dirichlet condition. So we just got the equations. We will actually solve them maybe in the next session after the simple algorithm is discussed. The second question is something which we discussed long back. It was the flow between two parallel plates. I've just non-dimensionalized this equation and written it here. So just to give a recap, so you have two parallel plates. Say this is at a higher temperature, this is at say Tb, and then there is flow coming up initially, or maybe I should, okay, if we consider it as to be fully developed, we know that it follows a parabolic profile. This is my x and y. So we are assuming it's a one-dimensional flow. So your continuity equation will essentially give you del u del x plus del v del y equal to 0, and if I assume it to be fully developed, this particular term goes off 0, and if I apply the boundary conditions that these walls are impermeable, your v essentially becomes 0. This is the fluid flow that you might have come across. So your x momentum equation will essentially give you rho times du dt will be minus dp dx. I am writing dp dx because along the y moment you don't have any terms, so del p del y will be 0, so p is only a function of x, and then you have viscosity terms. So since it is fully developed, you won't have x square term, so del square you get del x square. We just have this, and since it's steady, and then you don't have so if you see the terms here, so it will be del u del t plus u del u del x plus v del u del y. So this particular term is 0 because of v is 0, this is 0 because of fully developed, and we are assuming a steady flow, so this entire term LHS goes to 0. So now you are left with this equation. So now you can solve this equation with the boundary conditions, say y equal to 0 is 0, it's like no slip at both the plates. And if you solve this equation, you will get something like u equals some constant times y into say h minus y or something of this sort. So what I have done, this is for your velocity equation, and we kind of discretize this particular equation. If you observe, so you have something like, if you compare this equation with our scalar transport equation, general scalar transport equation, so you have a diffusion term mu coming up, and this is your source term. So we have discretized this, and we have seen that the solution from FEM matches with this profile that we have done previously. Now what we do is we will take the next equation, so we will take the energy equation. So the energy equation comes something like rho Cp dt dt, okay, d capital T is your temperature. Then we have del dot k del T, and then we also have some source terms. So this is essentially because of your viscous dissipation. So previously we have used the notation of phi. So this phi is essentially a viscous dissipation. So this equation essentially becomes something like, if for a steady flow and fully developed, so we have u times del t del x, and then v is essentially 0, so we don't have the next term, is k times del square t del x square plus del square t del y square, and this mu viscous dissipation term is essentially mu times du dy whole square. You can go through the derivation from the previous sessions we were had, how do we get this expression. So for now we'll just assume that this is expression we get. So what we do now is that we non-dimensionalize this. So say if I suppose define u star as u by, so here I will define u in a different way, so u by say u max, or I am non-dimensionalizing it with to some constant that will essentially give me u in terms of y times 1 minus y, essentially say y star times 1 minus y star. So this u star is essentially this particular profile where y star is given by y by h, and now I will non-dimensionalize the x as well in this h. So your x star will be essentially x by h, and to non-dimensionalize t I am using t minus t bottom by t top minus t bottom. If I try to non-dimensional in this particular fashion, the equation I will end up with, I am just removing the stars, say the quantities here are non-dimensionalized, so I am not writing stars here. So this will come out to be the equation that is shown in the question. So you will have a Peclet number. So Reynolds number is some Reynolds and Prandtl number. Reynolds number is essentially rho, this particular scaling u you get here by mu. Prandtl number is something that you are already aware of, so it's mu by alpha. And then you have Eckert number something here. This Eckert number is essentially, this EC is Eckert number that will essentially have some scaling of u square with respect to your thermal energy. So it goes something as this. So if you were to non-dimensionalize this equation, this is the equation you will be left with. So what this essentially tells you is this: if a Eckert number is too high, then only your dissipation term becomes significant, and for the Eckert number to be too high, you need to have very high speed flows. only when the flow is only when the flow speed is very high, this particular number comes significant and the second term will add up. So now we'll try to, now if we see this particular equation, so we'll take this equation. So just for simplicity, I will write this as some constant A times del square t, and then this as B times du dy whole square. Now if we compare this with our general equation, so this is my convective term, this is my diffusion term, and this is my source term, and we already know the profile of u, so we know u of y is essentially y times 1 minus y, so du dy is something we know, 1 minus 2y, so we can substitute this directly here. So the first step is essentially you discretize it, so your domain is this, you need to know the boundary conditions. So the boundary conditions are, at the bottom we have t equals to 0, on the top we have t equals to 1, and then we also need to know what is at the left and right boundaries. So initially, say suppose entire fluid is coming at this particular temperature, so initially t equals to 0, and on the outlet the condition is something that we do not know. So what we say is we will proceed till del t del x equal to 0. It's like in our previous examples, if you recollect, so we started out with this. So for a fully developed profile, we assumed for a velocity it is del u del x equal to 0. In a similar way, for a fully developed thermal profile, we sort of took the assumption that del t del x equals to 0, and then we solved this equation to get some results. But now we will see for this particular del t del x to be 0, the length of x should be sufficiently high. Or you might even observe the boundary condition is slightly different. Say if you have an adiabatic condition or something, then this particular case will not arrive also. That is something that is out of discussion. So we will try to discretize this equation. So we have u times del t del x is a times del square t plus some source term, yes. So if you were to discretize on our 2D grid on a general for an interior cell, so like the steps we have followed previously, we will also use the same things here. So the first step is a 2D grid. First step is to get your coefficients, that is your d little east, d west, d north and d south. So d east is given by if you recollect, so d east is essentially, if you were to do this, so you have del square t dv, so this will come out to be dot dA. So this will essentially give you a times del t del x in the east face, on the west face, north and south. I've just left down the areas here, so this will be correspondingly multiplied by the areas. So you have both of this multiplied by delta y and both of this multiplied by delta x. So if you group the terms, so d east is the coefficient of this, so that will be a times delta y by delta x. D west will also be similar, d north is delta x by delta y, and d south is. So once we get the diffusion coefficients, the next step is to get our convective coefficients. So f east, f west, f north and f south. F north and f south are quite straightforward. We do not have a v component here, so along this north and south we don't have any coefficients, so those will be 0. Along east and west, so this will be u east times the area. On the east face your area will be delta y, and similarly for the west one it will be u west times delta y. Now I have all the diffusion coefficients and the convective coefficients. So next time is to write our A east, A west, A north and A south. So to write this we need to fix on the scheme we will be using to, so when we write our original discrete equation, before writing this, if you try to write our original equation, it will be something like phi east, u east, in this particular case it is temperature, minus phi west, T west, phi north, T north, minus phi south, T south, will be written as in terms of D east, T capital E minus TP plus D south or D west, T west minus TP. We have D north on the face, T north minus TP, and then on the south face. And then we have a source term. This source term should be evaluated at P. So I'm just writing SP delta x delta y. Now we need to fix on the scheme that we will be using. Say we are using, so maybe it is right time to discuss about all the schemes. So we have discussed on central differencing or simply CDS, and then we have an upwind scheme, and then in addition to this we have two other schemes that we will be discussing during this session. One is a hybrid scheme and then a power law scheme. So it should be apparent here in CDS what we were trying to do. So we will write the coefficients in each of these. So first for CDS, your A east will be written as D east, and then you will have a term from here minus F east by 2. So these coefficients are again straightforward. Now we already know what this we already know what this D and F are, so we can directly substitute them and we can get these coefficients. So your AP is just the same, so it is sigma A in B plus F is minus west plus north minus south. The only problem with these coefficients, as discussed in lecture, is you might end up in some cases with negative coefficients. So to be more specific, say you can have, say consider the east coefficient. So this is DE minus FE by 2 can become negative if DE is less than FE by 2. So FE by DE is greater than 2. So this particular number is called, FE by DE is convective to diffusion, which we call the Peckley number. So if your cell Peckley number is greater than 2, then in this particular case your coefficient can become negative, and that can give you non-physical results. So because of this particular reason, we will not be usually go with the CDS scheme, central differencing, we go with the upwind scheme. So in upward scheme what we do is, the idea is this. So you have piece, east face and east cell. So I need to approximate the value of phi at this east face. So what we are doing is phi E, we are kind of taking from both east and west in central difference. This is initially when we were discussing about the types of equations. So for if you have an elliptic equation, it needs to take information from all the directions, and say you have an hyperbolic equation, it takes information only from, like, it has some directionality associated with the information flow. So when you have some flow happening in this particular direction, the information if the flow is sufficiently, like if the convection is much dominant than diffusion. Diffusion is where you have your elliptic nature coming into picture, and convection is where you just have an hyperbolic kind of thing. So this will essentially give some directionality. So information will, because of convection, if there is a velocity in say positive x direction, what that means is your information will flow only along the positive x direction. But if you have diffusion, then information can flow in both positive x and negative x direction. It is just random, it just happens in all the directions. So in central differencing scheme, we are just assuming it is diffusion dominant, and in an affine scheme what we say is phi e, the information cannot come from the next cell. So if the flow is in positive x direction, the information for the phase comes only from phi p and not from the phi east. So this happens only when your convection is significantly dominant than diffusion. So that is exactly the case we are seeing here. So in CDS, if you see the Peclet number is essentially the ratio of Fe by dE, that is convection by diffusion. So if this is greater than 2, or which means if the Peclet number is too high, where the diffusion effects are neglected or diffusion effects are small, in that particular case you should only consider information to be flowing in one direction. So you should just take the affine scheme. So if you just use affine scheme, like you can see, like this is second order accurate and this is just first order accurate. So using affine scheme is not always that good, so we just use some hybrid scheme. So what we do in hybrid scheme is just we check for the cell Peclet number for every cell. So if the Peclet number is say greater than 2, then we go for an affine scheme. If it is less than 2, we just stick to the central differencing scheme. That is your hybrid scheme. The next version is power law scheme. The idea here is why should we stick to just 2? We can actually go little further. So this goes as high as the value of 10, only then it will consider affine, otherwise it just sticks to series. But we cannot always use this if-else statements. So when we do it, we will see maybe at the end of the session how to do it programmatically. Like when you do it in a program, how do you implement it actually? So that we will see maybe at the end of the session. So now we have all these equations. The only thing is the boundary conditions. So for interior cells it is straightforward. So we have APS sigma A and B. We don't have any source term here. So maybe I'll write for one boundary and then leave the others as an exercise. So we have, say, on the bottom boundary, we will write on the bottom boundary, or maybe on the top we have a Dirichlet condition t equals to 1 on the top boundary. So if you were to write on the top boundary, your A east term should remain the same. Say if you are using central differencing, dE minus Fe by 2. Your A west also remains the same. A north is essentially 0 because it is a boundary, and A south will remain the same. If you write AP as sigma A and B plus now, because of this boundary, in addition to this you need to have some additional terms. First term coming because of diffusion. So since it is a boundary, you will be dealing with some half cell there. So because of that half cell, you will have a 2dn term coming up, and then one additional term coming because of your phi north. The boundary value is specified, but you are taking an additional here, so you need to subtract it. So this will be your AP term. Since the value of phi and B is specified, you will also have your B term coming up. So the B term will essentially ideally be 0 because you don't have any source terms. Now because of your Dirichlet conditions, you will have 2dn minus Fn times whatever is the boundary value. So this will be your B term. Now similarly on the bottom boundary, you have t equal to 0. So AP will come same. Instead of the north coefficients, you will be having south coefficients, and then this particular term will go to 0 because on the south boundary we have t and b as 0. I guess this is clear. There are any doubts, then we can maybe pause for some time. Yeah, I guess there are no doubts. So we will see the programmatic implementation a little later. The third question is again some question that you might be familiar with. So we have a parallel flow heat exchanger. So we will consider the non-dimensionalized equation for a parallel flow heat exchanger, and then we'll have to solve that. Okay. This is slightly different from what we were discussing till now. So instead of one equation, we have two, we essentially have a coupled equation. So if you recollect your parallel flow heat exchanger, so you have a hot fluid, and then you have a cold fluid. So this is TH in, TC in, TH out, and TC out. The non-dimensional temperatures can be written as dTH by dx is essentially Tc minus Th, and dTc by dx will be Th minus Tc. And your boundary conditions are, say, initially this is non-dimensionalized, is 1 and 0, and these are something that I do not know. So till now, whatever problems we are solving in space dimension has as boundary conditions, we need to know both these values. But in this particular problem, in case of a heat exchanger, so we already know for a parallel flow heat exchanger, the temperature will drop something like this as a function of x. So this is for the hot fluid, this is for the cold fluid. But when we try to solve the problem, we would be only knowing the initial inlet conditions but not the outlet conditions. So if you know one of these outlet conditions, then you can use the energy balance, and then you can directly determine the other temperature. But say suppose we do not know, we just know the inlet conditions and we know this differential equation. So how do we go about solving this? So our boundary condition are just Th at x equal to 0 is 1 and Tc at x equals to 0 is 0. These are my only conditions given. So if you compare this with your so like previously when we were discussing how do we deal with coupled equations, so we will write a new matrix capital T as THTC, we'll just write in this way. Then we will write our dt dx as some matrix. So you have minus 1, 1, 1 minus 1 times THTC if I write in this particular way. So this boils down to Tc minus Th and Th minus Tc. So I'll write this as some matrix A. So this is again your standard equation. So dt dx is A times T. So if you compare this with our convective diffusion equation, so we have plus Sc plus Sp free. So if you compare these two equations, so you have rho u bar essentially turning out to be 1, though it is a matrix, I am just writing for simplicity. So this is 1 and your gamma is essentially 0, your Sc is 0 and Sp is essentially your matrix A. So if you compare with this equation, so how do we go about solving this equation? If you were to solve in a traditional way of say if we go with the straightforward way, you just take a domain x equal to 0 to whatever length you have, x equal to L, and then you discretize it, you take cell centroids and then write these equations. But then what you will be left with is finally you will have n equations, but then you don't have your boundary values. You just know this boundary value and you do not know this boundary. So you will not be able to solve all the equations. You will be left with an indeterminate system. So the idea here is something that we have discussed previously in the case of affine scheme. So if you see the Peclet number here, so that is essentially your f by d. Diffusion is essentially 0 in this particular case. So this turns out to be infinite. So when your Peclet number is infinite, your information will essentially flow in only one direction. So this boundary will not affect any value that is preceding this. So the value at this last cell is only influenced by the previous cell but not from the boundary. So this is something what you call a one-way coordinate, or in this particular case it's a one-way space coordinate. This is something which we are very familiar with time. So when you have your time, when equations are written in terms of time, you know something in the future is not going to affect something in the past. The idea is very similar in case of space here as well. In whatever is happening at further point in the space is not affecting this, because your convection is much dominant here, or essentially your diffusion is zero. Only diffusion is something that mixes up things from here and there. As long as diffusion is not present, your information will flow in only one direction. So in one-way space coordinate, this essentially means you are treating x as t. So this becomes our standard equation. Then you have dt dx equal to at is something that we know already of. So if you treat this as time, then you can use any of the methods which we discussed. So you can use Euler method, it's either implicit or explicit, or we can stick to our Crank-Nicolson scheme. So we'll say we will use Crank-Nicolson scheme. So this becomes dt dx, we will write this as t at x plus delta x minus t at x by delta x. It's like previously when we were discussing, so it will be half times t at x plus delta x, and then we have t at x. So now you have your equation t at x plus delta x is tx plus so this is an implicit equation, and you can solve this equation to determine your value, or to be simpler we can just stick to Euler method. So you have tx plus delta x is essentially given by tx plus delta x times a times t at x. So since the initial value at x equal to 0 is given, using the value at x equal to 0, you can determine t at delta x and 2 delta x and so on till whatever value you want. So the only point that I want to highlight here is when you have your diffusion component to be negligible compared to your convective component, you can treat that space coordinate as a time coordinate and use any of the methods that we discussed previously, like Euler implicit, explicit, or Crank-Nicolson schemes. I hope that is clear. And the exact solution is something, okay, I haven't derived the analytical solution. So the analytical solution is something you know of. So it goes something like this. So if you were to solve these equations analytically, I just want to show the results so that we can compare the analytical with the numerical results. It's Tc minus Th. So we just add these two equations, you get something like H plus Tc is essentially 0. So you have Th plus Tc equals to constant, and if you supply the initial condition, so that will be equal to 1. So substitute it back, you have dTh by dx equals Th minus Tc, that will give you this. So you have dTh by minus 1 is essentially dx. You just integrate, so you have ln 2Th minus 1, varying from initially 1 to some value. Okay, I forgot the 2 here. So did I write the equation wrong? So it's Tc minus Th. Yeah. For the hot one it should cool, and for the cooler one it should get heated up. Th minus Tc. So you have a minus plus, so you have a minus 2x. Since Th is this, your Tc will be 1 minus e power minus 4, 2x by 2. So we will compare this solution with the numerical a little later. Fourth question is again straightforward like the one we discussed. So the only difference is till now we are discussing with only you need a one-dimensional velocity. Now we have both u and v components, and all the while wherever we are discussing, it's as if we know the velocity components. However, maybe in the next week we will discuss when velocity is your unknown. In this particular equations, it's as if you know the velocity already. All the velocity values are given to you, and then you are solving only for your scalar phi. So the boundary conditions are also given. All of them are Dirichlet conditions. So you have, so if you write the domain, so you have at y equal to 0 is 100. So this is x equal to 2. It's 0. Y equal to 2 is 0. Y equal to x equal to 0 is 100. So this is the domain with the boundary conditions. So we'll use central affine and hybrid and power law. So this is again straightforward. This is very similar to the question we discussed in the second question. So you just have a and b terms. Maybe we'll write the equations down. So you have phi as 100, 100, 0, 0, and your equation is A is given as 10, B is given as 2, gamma is given as gamma and rho are 1. So the first step, like as we have discussed previously, is to write your coefficients. So your d east will be gamma delta y by delta x. So in this particular set, it's a 2 by 2 grid, and this is 2 comma 0. So essentially your delta x and delta y are 1. So d east is 1, d west, d north, d south are also 1. Next is to write your convective coefficients. So f east is u east times delta y. U is given as 1 and v is given as 4. So this will be 1. F west will be 1. F north is again vn times delta x, that is 4, and F south is vn times delta y. Now we have both the diffusion and convective coefficients. We are good to go with the other coefficients. So we have A east. Okay, now we have different schemes we need to write for. Okay. First one is central difference. So maybe I will, okay. So before fixing on the scheme, the general way of writing this is A east is written as some function of Peclet number times d east plus, if you recollect from the lectures, it will be 0 comma minus fe. So we will elaborate this a little. So this capital A is a function that is chosen depending on the type of scheme. So as we discussed previously, the type of scheme you choose depends on the cell Peclet number. If your Peclet number is too high, then you might be good off with using upwind scheme. If your Peclet number is too low, then diffusion is dominant, then you have to be choosing a central differencing scheme. If your Peclet number is somewhere in between, you have to use some kind of an interpolation between these two. So that is something that has to be taken care by this function A. So what this function is, say if you are using central difference scheme, this turns out to be or maybe we'll write the formula later, we'll compare and then write the formula. That will be easy for you as well. So first one is CDS. So if you were to write CDS scheme in central differencing scheme, A east is d little e minus fe by 2. So if I compare this with the above formula, so I can write this as dE times A of PE plus max 0 comma minus fe. So in this particular case, fe is essentially 1 here. It's like the flow is in the positive x direction, so the maximum value will be 0. this equals dE into 1 minus Fe by dE times 2. So your A has now become 1 minus 0.5 times PE. So this is for central differencing scheme. Say you are using an UDS. If you are using UDS, your A east will be given as D east. In affine scheme, you will have a term Fe only when the flow is along. Okay, let me write it. So you have dV, dE, and then you have max of 0 comma minus Fe. This is the general formula for an upward scheme. When you have, if your Fe is positive, that means your flow is in the positive direction. So this is your P, little e, capital E. If flow is along this direction, so you won't have a contribution from the east face unless flow is in the opposite direction. Only when Fe is negative, that is when you will have a contribution to your A east term from this. Otherwise it won't have any contribution. So when Fe is positive, that is along this direction, then you shouldn't have any contribution from that. So that is why we have written max of 0 comma minus Fe. So when Fe is positive, this becomes negative and the maximum will be 0. So if Fe is negative, in that particular case this will be positive, and then you will have a term contributing to AE. So AE will be dE plus Fe if Fe is negative. So for a UDS, we have A of P essentially given by 1. So it will always be 1, and then you just have just this term. So if you are using an hybrid scheme, now you have two things to decide. So like previously we discussed, if P is greater than 2, you go for an affine scheme. If it is less than 2, you go for a series. So for affine scheme, A value is 1, otherwise you have a value of 1 minus 0.5 times PE. So we have these two terms here, so we write this as 1 minus max of 0 comma 0.5 times PE. So whichever term comes, so if you have a very high value of Peclet number, this will be the dominant term. If you have, so if you have a very high value of Peclet number, so say it is greater than 2, if your Peclet number is greater than 2, this term will be greater than 1, and then you will be left with, maybe I have to write it 2 here. So if this is greater than 1, then that particular term comes also. Say if P is greater than 2, then you will be max of 1 comma 0.5 PE will essentially give you 0.5 PE. If it is other way along, if Peclet number is less than 2, max of 1 comma 0.5 PE should give me 1, so that you don't have any contribution from this. Power law is something different, where you will be considering 0.1, so that your Peclet number, you will go as high as Peclet number 10. We will leave power law for now, but I think it is clear till hybrid. Or you have any queries on this? I think it is clear. Maybe we'll see maybe it's already 6:30, so maybe we'll see some of these codes so that you will get clear how to implement them. this is for the case of the parallel plate flow. So I've just find for people who are familiar with Pythons, like we have been going through C++ for a long time, so I thought it will be quite easy to explain through Python as well. So we have the profile of u given by y times 1 minus y, and then you have a du dy, that is 1 minus 2y. The problem parameters I have chosen to be Eckert number to be high compared to your Reynolds number, as close to Reynolds number, so that your viscous dissipation term is dominant, and these are your boundary conditions. So L is sufficiently large so that you can attain your fully developed flow. So I've chosen some mesh parameters. You have nx and ny. I've chosen different line along x and y directions, and then you just take dx dy. This x and y are just the coordinates of the cell centroids. The first step, as we have been discussing, is to define your diffusion coefficients. So you have all the d's on all the faces, that is delta y times your diffusion coefficient in this particular problem is 1 by Reynolds number times Prandtl number. So I have taken that. Once you get the diffusion coefficients, the next step is to populate your convective coefficients. So for this problem, like as we have discussed, f east is given by u east times delta y along the vertical direction. F west will also be there, but f north and f south will be 0 because we don't have the v component of the velocity, and your b essentially is a source term coming because of your viscous dissipation, that is Eckert number times this, and then you have a du dy whole square times delta v is dx dy. Once you have all the coefficients, now there are different schemes. So I am using an upwind scheme. So in an upwind scheme, you have a east given by d east plus maximum of 0 and minus fe. Similarly, a west, a north and a south. There is just a minus n here just to take care of your convection. So if you are thinking of an east face, it should be, you will have a contribution from the east face only when the flow is coming in the direction opposite to it. On the west face, you will have a contribution only when the flow is along this direction, along the positive direction. So for the east you will have a minus, and for the west you will have a positive, and similarly for the north and south. These are for all the interior cells. Now when you have the boundary cells, you need to make the appropriate coefficients to 0. So on the east face I have made a east to be 0, west and north and south respectively. So once I have done with that, the next step is to populate your AP matrix. AP is essentially sigma A and B plus this particular term will be 0, but still be, just for the sake of consistency that we are doing, we will just add that. So you have f east minus f west plus f north minus f south, which will ideally be 0 because we are dealing with incompressible flows. So this is essentially the continuity equation, that if you discretize your continuity equation, this is the term you will be left with. However, we will just follow the notation we are using. So now we will do each on the boundaries. So on the east boundary, we have it's like a fully developed flow where we have a Neumann kind of condition, so it shouldn't have any contribution, so I have just put 0. On the west face, however, we have initial Dirichlet condition given. So whenever we have a Dirichlet condition, we will have some terms contributing from because of Dirichlet condition. So for the diffusion term, we need to add 2 times the diffusion coefficient, and for the flux we just need to say we have subtracted minus Fw here, which ideally shouldn't be there. So for the diffusion term, we will have 2 times diffusion, and then we have a minus Fw term coming up here because of your flow. Since it's a Dirichlet condition, the term should not be there. Just to compensate for this, I have added another Fw here. And similarly on the north and south faces. On the north face, again we will be having a Dirichlet type of condition, that is essentially your temperature condition is given as T equals to 1. So you have this, and then you don't have any flow conditions. Similarly on the south face. So I think this is quite straightforward. Now coming to your source terms will get added as and when you have Dirichlet conditions. So you have Dirichlet condition on the bottom boundary and on the top boundary. So on the bottom boundary the value is T equals to 0, so you just multiply that coefficient with 0, and then on the top boundary you have a coefficient of 1. And since these flow coefficients are 0, I have not added those terms here. Next step, I have just checked whether the coefficients satisfy the Scarborough criteria or not. It's like you just take summation of all these coefficients divided by AP, sigma A and B AP. If it is less than or equal to 1 or not, I have just taken this, and whatever, if it is not equal, if it is greater than 1, then I've just stored in this particular variable, and when I've printed it, the particular value is coming to 0, which means the square bar is satisfied for all of these conditions. So which means you can solve this using Gauss seidel. Now we have a 2D problem, so you can either use a normal Gauss seidel and solve the complete equation, or you can use line by line PDMA, or you can go with the PDMA algorithm that we have discussed previously. Here I've just used the Gauss seidel since it's the easiest to implement of all. I'll just take the Gauss seidel is straightforward, so you just iterate through x and y directions, and then you keep on updating them one by one, and then accumulate error. As and when the error is greater than your tolerance, you just stop the iteration. So I've taken a tolerance of around 10 power minus 6. These are the solutions I get. So the only point that I want to highlight here is the temperature. You can see we have non-dimensionalized the temperature, and the temperature should be between 0 and 1. That is something that is happening on the boundaries. So here you have something close to 0, and on the top you will have something close to 1, but in between is where you have temperatures that are much higher than both of these boundaries. So this is essentially because of your viscous dissipation, that is continuously adding energy and then increasing your temperature in the interior region, in your core region. So as in, if you decrease your length to say 20 instead of 200, sorry, so you can see the maximum temperature is again reduced. So the only point that I want to bring here is as you keep on increasing your length, as you progress along the length, your temperature keeps on increasing. So it so happens that dTdx may not be 0, so that the fully developed assumption that you are taking for a velocity is quite different from the fully developed assumption that you should be taking for temperature. So for fully developed temperature profile, you cannot just say like del T del x equal to 0. You need to, which we have done previously. But that is quite a good approximation only when you have your Eckert number as low. So here the Eckert number is taken to be too high. So if suppose Eckert number is low, so if I reduce it by 3 orders of magnitude, then you won't have any significant increase in your intermediate temperature, so you can have the normal profile. So in that particular cases where your temperature will be between 0 and 1, in those situations you can make the assumption like del T del x equal to 0, and then just solve it as a normal diffusion equation. So you'll have some linear temperature profile. I think this is clear. So this is for the parallel flow heat exchanger. It's again straightforward. So I've just taken the A matrix here, like dTdx equal to A times D, that is the governing equation we were having. Your A is given by -1, 1 and 1 minus 1. So I've just defined some constants here so that it will be a little easier later. So here I assume we will be following say Euler method, or you can use any of the method of your choice. So I think I've used Crank-Nicolson method. Yeah, the question asks you to solve using Crank-Nicolson, so I've just taken Crank-Nicolson. But you can use any method of your choice and see how this converges with. Maybe I'll leave this as an exercise. So you can compare your analytical solution with your numerical solution. You will naturally find these fluctuations. That is just because I've considered very low value of n. So if you increase this, the fluctuations will gradually die down. Fluctuations will keep on reducing. The error is there because I haven't used the Newton-Raphson method. You can use a second order method to essentially, or you can use the same Gauss seidel method to iterate it again, which I haven't done for this particular question. So you can try that later. Question that I want to highlight is for this particular question that we were discussing. So you have Q equals to 1 and V equals to 4. So it's a 2 by 2 matrix. So first step, as we have discussed, is you need to get all your diffusion coefficients. Okay, so you have gamma times dy dx dx dy, and then you have f east is given by rho times u times delta y. East and west will be in terms of delta y, and north and south will be in terms of delta x. Your Peclet number is given by f by d, convective by diffusion, so f by d. Now in the central difference scheme, when you are implementing, like we have seen for an east phase, it will be d east minus fe by de plus fe by 2, or so d east minus fe by 2. So this is that particular term here. So if you expand this particular term here, so this specular number will come out to be fe by de. So this can be written as d east minus fe by 2, plus you have another term here. This term will come up only when you have your flow in the opposite direction. So essentially only when your fe is negative, this term comes up to compensate for this. So if your flow is in the opposite direction, so this fe term will try to add to this, and then it will, so this will be minus PE and then you will have a minus half here. So PE will be negative, and then it will be left with DE plus FE by 2. So that equation will remain the same. This is for a CDS, central differencing scheme. Now if you want to go for an upwind scheme, so the expression will be same. The only difference is you need to remove this, replace this with just 1. So you will have this maximum of 0 comma minus FE. FE I am writing as minus PE times DE. You don't have these terms. This is in your upwind scheme. Now in hybrid scheme, what we do is, like we have discussed just now, so you'll have a contribution from my half of PE. The hybrid scheme, the idea is as and when your peculiar number is greater than 2, because in central differencing scheme we have seen that if peculiar number is greater than 2, your A east and A naught coefficients are becoming negative. So to avoid that, as and when your peculiar coefficient is greater than 2, you use the upwind scheme instead of central differencing scheme. And why are we choosing central differencing scheme? Is because it is second order accurate, while upwind scheme is just the first order accurate. So this particular term 1 minus 0.5 into this, if peculiar number is greater than 2, this term turns out to be negative, and in that particular case both the terms cancel each other, and then you will be left with the scheme very simple. Like this particular term will give you expression similar to your upwind scheme, and when peculiar number is less than 2, this particular term will be greater than 0, and then the term will get added up to the previous one, and then you will have an expression very similar to central differencing scheme, something like this. You can see the expression here. Say maybe I'll write for one of the case. Say if peculiar number is greater than 2, in that particular case you'll have DE times maximum of 0 comma your, if peculiar number is greater than 2, this particular number will be negative, so the maximum will be 0. So you have DE times 0 plus you have maximum of 0 comma minus FE. So this is something very similar to your upwind scheme. There needs to be a 1 here. Now if peculiar number is less than 2, you have DE times 1 plus the maximum of these two will be the other one. Since peculiar number is less than 2, you will have a positive coefficient. So and then since this will remain the same, if FE is positive, so this term will be 0. Okay, so this should be similar to your central differencing scheme. Okay, there shouldn't be a 1 here. Yeah, maybe I think I made a mistake while explaining. Okay, say for upwind scheme, when peculiar number is greater than 2, you have DE times the maximum of these will be, okay, maybe the 1 should be outside of this, so it will be 1 minus this. Okay, so this particular term will be negative, and then you will have a 0 coming up there, and then you have maximum of 0 comma minus of V. So when you have higher Peclet number, your diffusion effects are negligible. So you are neglecting your diffusion, and then you are just taking your source, taking your convective terms. Should have one here, or maybe I'll give you the exact expression. Power law scheme is also very similar. The only difference is instead of 0.5 you will be taking 0.1 here. Maybe I will show you the exact thing here. So when you have so this is expression that goes off with the power law scheme. So we have 0.5. So the idea is, if you take an approximation of this, so we have 1 minus 0.1 whole power 5. So this goes as 1 minus 0.1 times P whole power 5. This is actually approximated, can be approximated as 1 minus 0.5 times Peclet number if your Peclet number is small. So the second one is your hybrid scheme, and the first one is your power law scheme. That is the only difference between these two, but power law scheme seems to be more accurate than your hybrid scheme, but it is computationally a little expensive. So we haven't seen this problem, so maybe I'll leave this aside. Okay, are there any questions till now? We have around 15 minutes left, so if there are any questions I may take it, otherwise we will go to the next questions. I assume there are no questions. We have 15 more minutes. So why are we resorting to hybrid and power law or other schemes? So say suppose we consider the equation. Say we don't have any source terms. So I can write this equation as say we solve for a one-dimensional problem. So you have, okay, it's just one dimension, so I'll just write it as and it is straightforward to solve this equation. So if you were to solve this equation, So this particular term rho u delta x by gamma, if you see in one dimensional case, so you can write this as rho times u is essentially your convective term, gamma by delta x is essentially your diffusion term. So this is essentially my f by d, so this is my Self-Peclet number. See, the phi goes as an exponential profile, so that is exactly the question that we will be discussing next. So you have a profile, but here the source term is not equal to 0, you have some finite source term. So the question asks you to dimensionalize the non-dimensionalized equation, and then you obtain exact solution in terms of A1 and A2. Once you obtain the exact solution, till now we are using CDS scheme where you have a little e, we are using some linear approximation. So we are using some linear approximation for phi e as phi east plus phi p by 2, or in case of an affine scheme we are using phi east, and so on. All of these are linear, all are linear profile assumptions. The next part of the question asks you to do an exponential profile assumption instead of linear profile assumption. What happens if you use an exponential profile, and then you write the equations for AP, and then we try to compare both these methods and see how the results are matching with each other. That is exactly the first question. So by exponential profile, so you have say this is E, PE, and this is my east face. So what I was asking is, you have phi E minus phi P will go something like the idea is, because your analytical solution is essentially giving you phi as an exponential function of Peclet number instead of your linear functions. Like in all our assumptions we have just taken linear profile assumption. So if we use this profile, can we get a better solution than the linear profile assumption? So that is essentially the part of the next question. So it happens that your exponential gives you an exact or a better solution compared to your linear profile assumption. The only problem is it is computationally more expensive than your normal one. So what we do is use some of these approximations. So if you see this exponential term, so if you have very high Peclet number, say if your P is too high, then you can kind of divide it with PE, and then you can kind of come up with this term will go to 0, and then just divide with exponential of PE. So when you have very high Peclet number, this will essentially become 1, and then it will become kind of your linear profile assumption. So only when you have very high Peclet numbers is when your exponential profile can be approximated as a linear profile that is very similar to your affine scheme. You will have high Peclet number when you have affine scheme. So when your convection is dominant in those particular solutions, your affine scheme will give you better results. If your Peclet number is low, then your affine scheme might give you, it will give you physical results, but then the deviations from your exact solution will be quite high. So we'll go through this solution as well. So for those of you who are familiar with symbolic, just to derive the analytical solution, you can use a symbolic, any of these symbolic tools to do that. So Gauss-Seidel is again straightforward. The analytical solution is where the question gives you some values of A1 and A2. I have just taken some values, and then you can, this is your differential equation, and then when you solve, you get the analytical solution. That is straightforward. Central differencing is where you have these terms. So your east coefficient will have your diffusion plus your convection term, Fe by 2, and then for the west coefficients you have minus Fw by 2, and AP is essentially the summation of these two. So I've just considered how many cells, around 20 cells. in this particular case your AP is essentially, when you add these two, your F is and Fs will cancel off, so I've just written 2 times the entire coefficients. So for the boundary cells you have east and west boundaries, you equate the coefficients to 0 and appropriately update your AP values. Your AP will have an additional term. So in this particular case your boundary conditions are Dirichlet conditions, so you have a 2 times term coming up. B is your source term, so here we have a source term A1 given as 10 times dx, plus this another term is adding up because of your Dirichlet condition. So whenever you have a Dirichlet condition, you will have a 2 times diffusion coefficient times it. In this particular case, diffusion coefficient is 1 times your phi value is essentially 1. So you solve it using central differential scheme. So if you see the solutions, your central differential scheme is actually kind of underestimating this at this particular value. But if you were to use an upwind differencing scheme, you would see like they will be close to each other, except when you have very high diffusion. So initially for very low values where you have significant amount of diffusion is where you find these deviations between both of them. Otherwise your UDS should be equal to your exact. But if you use an exponential scheme, they will kind of match with each other throughout your domain. So this is where I have just assumed your exponential profile like I have shown now. So when you use an exponential scheme, both of them are very similar to each other. But these results are only for this particular chosen value. So if you use some different values, then they might just change. It's like before actually performing the solution, you cannot right away tell which one of them is actually better than the other. So I've tried for different values, and the question asks you to try for various values of A1 and A2. Your A1 and A2 are essentially your diffusion. One of them is diffusion and one of them is diffusion, other one is a source term. So by varying these things, you can see when is your central differencing working better than your upwind and when the other way. So in some situations you can actually find central differencing to be more accurate compared to your upwind differencing scheme. That is essentially when your diffusion coefficients are much higher. But your in all these cases your exponential will give you much better solution compared to both CDS and UDS. So that is something I would highlight maybe in the next question. So I am not discussing this question since we are almost out of time. So around 7 minutes. I will go through the question later, but I will just show you some of these results. So if you see the UDS is kind of underestimating. It always happens that only when you have sudden changes. UDS has something called diffusion property. I think that is covered in the lectures. So because of this diffusion property, any sharp changes or sharp bends will be underestimated by UDS because of the diffusion nature. So these sharp changes will not be captured by UDS but can be captured using central differencing scheme or any of the other schemes that we discussed, hybrid or power law schemes. This is only for very high values. So if I decrease this value, decrease the number of cells, okay, the sharp turn is coming after this, so it is not captured by that. So maybe we will decrease it further. Yeah, you can see each of these getting deviated. Your UDS will not be able to capture any of these sharp things. Whenever you have any sharp change or something, it will tend to be diffusive at those zones, and then it will try to give you the value will be different from the other ones. So when you have something of sharp nature, you need to be choosing some other scheme like hybrid or a power law, so that you will get better approximations. Yeah, we are almost about time. We have around 5 minutes. So if you have any questions, we can discuss. The last question is actually quite involved, where you have a duct. However, the duct is porous, so because of the porous nature of the duct, you will have some leakage, either inflow or outflow. So this is essentially going in this direction. So you want to, in the absence of any pressure, just because of your diffusion and your convective term, so you have to solve this equation for two different cases: when the flow is actually coming into the duct through your porous walls, and when the flow is actually leaking outside. So this is one case, and the other one is when you have leaking out. So it will be very similar. The only difference is you have, in addition to your this leakage or your seeping in, is essentially will be added to your source term. Your diffusion term and your convective term are the same. So we just have 3 minutes. So we will discuss this problem maybe in the next class. We'll discuss this, and we'll also start with simple in the next session, next class. Yeah. Thank you all. So there are no questions, and I think we can conclude for today. Thank you.